So, welcome to this course on Theory of Plasticity for Engineers, Concepts and Applications. In this module, we are dealing with computational aspects of plasticity. In this lecture, we are going to understand how to come up with a finite element formulation for performing elastic plastic analysis. The outline of the lecture is as follows. We are going to discuss finite element formulation of the elastic plastic boundary value problem. We are going to understand incremental iterative solution approach. We are going to discuss how to compute algorithmic tangent modulus and implement the return mapping algorithm. And we are going to discuss stability for elastic systems and stability of elastic plastic algorithms. First, let us discuss how to formulate the finite element formulations for elastic plastic boundary value problems. So, the formulation starts with a weak form or a variational form of the boundary value problem, and we are going to assume homogeneous displacement boundary conditions. So, the u is equal to u bar and is equal to 0 on the Dirichlet boundary, and the loading is prescribed through body forces and tractive forces. So, we can have the body forces and the tractive forces denoted by sigma bar on the Neumann boundary. The displacement fields satisfy local constitutive equation at all stages of loading, and the displacement field is given by u comma t, and incremental iterative approach is considered, and inertia is neglected in this formulation, and the quasi-static incremental algorithm is given by g of sigma comma eta must be equal to 0. Now, we discretize the domain into number of non-overlapping elements. Each element is defined over a small elemental domain. We are discussing here a one-dimensional situation where the domain is of a length of a bar whose length is given by L, and the whole domain is essentially an assembly of elements. So, the total number of elements in the discretization is NEL. Any typical element is starting from XE to XE plus 1. And at the boundary nodes are at x1 is equal to 0, the end nodes, two end nodes are going to describe what is the xn element plus 1 will be equal to L, and then we are going to have several number of elements. The total number of elements is NEL, and a typical element is having a size HE, and which is described between XE and XE plus 1. So, the element length is defined by XE plus 1 minus XE, and this element size HE is assumed to be uniform throughout the discretization. So, we start by confirming finite dimensional space. So, the approximation is denoted is belonging to this VH, and any typical element, the approximation that belongs to this space VH is given by WH, and we do a interpolatory, the finite element approximation is interpolatory in nature. So, a typical finite element approximation between XE and XE plus 1, which is HE, is denoted by so, this is going to be your NE1, and which is linear approximation, and this is denoted by NE2, and between these two approximations we are going to have WE1 is the first value. So, this is the at XE the value is WE1, and at XE plus 1 the value is WE2, and between these two the approximation is given by WEH is equal to NE1 WE1 plus NE2 WE2 is a linear approximation, which is approximating linearly between the two nodal values defined at Xe and Xe plus 1, and He is the size of the element. So, WE1 and WE2 are the two nodal degrees of freedom, and the global continuity is ensured by node matching. So, essentially if there is another element beside that, so we are going to have these two values. If I call this as WE minus 1 2, and so this value is at Xe is going to be same. So, WE minus 1 at 2 is equal to WE1, and similarly at this node for the next element I am going to have so WE plus 1, so this is WE plus 1 is equal to WE plus 1 is equal to W2. So, the next elements that we are going to have, so if I call this as He between Xe and Xe minus 1, and Xe plus 1 and Xe plus 2 is the next element. So, we are going to have nodal compatibility of deformations at the common degrees of freedom. So, the functional is evaluated element wise. So, the functional is written as in a discrete form as summation E is equal to 1 to NEL GE sigma H comma WH. For a typical element, one can calculate what is the derivatives of the displacement, which is denoted as dou by dou x of WE of H. So, which can be denoted as BE times WE, where BE is called as the strain displacement matrix, which is denoted as minus 1 by He comma 1 by He. So, the element contribution can be now written as GE of sigma H comma WH is equal to WE transpose times FE internal minus FE external. So, the element internal force can be written as FE internal of sigma H is defined as integral over domain of element B transpose sigma times dx. This is the strain displacement matrix, sigma is the stress. So, B transpose sigma integrated over domain dx will give you FE internal, and FE external can be calculated as the contributions coming from the traction forces and contribution coming from body force. So, this is a term coming from body force, and these are terms coming from tractive force. So, N transpose rho times B dx is going to give the body force part, sigma bar T times N transpose evaluated on boundaries of the element is going to give the traction force. And using the assembly conditions, which says that the equilibrium of forces are going to be satisfied at the nodes, equilibrium and compatibility of displacements are satisfied at the node at common DOFs. Using that condition, equilibrium of forces and compatibility of displacements are satisfied at common DOFs. We can assemble the individual element equations to get the global functional written as W transpose F internal minus F external, where W transpose is a vector of all the nodal displacements, and F internal is essentially obtained by assembling all the internal forces, which is denoted by A times summation E is equal to 1 to n elements Fe internal of sigma H, and F external is equal to A times summation E is equal to 1 to n number of elements F external of T. So, the inertial term is computed element by element exactly as for the static term. So, we can write inertial term as density times acceleration times the test function. So, we get W transpose md double dot as the inertial term. The global mass matrix is obtained by standard assembly procedure, where individual mass matrices are denoted as MEAB is rho times n transpose times n into dx. So, this is called as the consistent mass matrix. Using the consistent mass matrix in this expression, we can assemble to get the global mass matrix. So, this is going to be diagonal, and we can evaluate using quadrature rules. So, the finite element counterpart of the weak form of the momentum balance will read rho dou square UH by dou T square WH dx integral over the domain plus g of the functional g of sigma h comma WH is equal to 0 for all WH belonging to the admissible set of functional space BH. Where WH is arbitrary, the coefficient vector W is also arbitrary. So, following the discretization and assembling the individual mass and internal force and external force, we can write the discrete set of equations as md double dot plus F internal in terms of sigma h minus F external of T must be equal to 0. Now, one can calculate the stress field within a typical element using strain displacement matrix and using the distribution of stress, and the internal force can be calculated using numerical quadrature as summation over the number of quadrature points B transpose sigma h WL where XL belonging to B denotes a quadrature point, WL is its corresponding weight. So, an integral of the form f of x dx, which is evaluated from minus 1 to plus 1, is denoted as summation I into number of Gauss points, weight at that Gauss points times the value of function at that particular Gauss point. So, in numerical integration, we are going to evaluate an integral of this form as an algebraic sum of a linear combination of weight at a specific location of the Gauss point times the value of function evaluated at that Gauss point. So, here WL is corresponding weight, and n integral is the number of integration points that we are going to have, and XEL denotes the location of the Gauss point. So, this is going to be like the xi I, which is going to give the location of the Gauss point where we are going to evaluate the integral, and this WL is going to be the weight associated with that particular Gauss point. So, one can use a parametric approach to write the quantities in terms of a local coordinate system that is local to the element. So, when you have a typical element which is going from xc to xc plus 1 in a parametric form, so this is going to be He. In a parametric form, one can choose a coordinate system xi which is going from 0 to plus 1 on the left hand side to minus 1 on the right hand side, and this total length can be of 2 units, and one can write all the shape functions in terms of this natural coordinate system in terms of xi. So, the stress field inside the element can thus be calculated, and the quadrature points can be specified, and one can have 1 point quadrature rule, 2 point quadrature rule, or n point quadrature rule to evaluate integrals of this form which are going from minus 1 to plus 1. So, one can restrict the attention to static problems right now to discuss the incremental solution procedure, and we neglect the inertia terms, and the quasi-static elastoplastic problem solution is discussed now using an incremental iterative procedure. So, essentially what we are going to have is, when we talk about a load versus deflection or stress versus strain, and we have a plot like this, which is nonlinear. We are going to follow a incremental procedure where we are going to divide this as into number of steps, where P1 is equal to P divided by N, where N is the number of steps into which the load is divided, and we want to achieve an equilibrium solution that is corresponding to P1, which is delta 1. So, this is the increment that we have, and following an iterative procedure starting with an initial stiffness and reaching this equilibrium, we can then iterate on the solution, and this iteration is followed in a manner where the stiffness is going to depend upon what is the state of the loading that we have, or the stiffness can be a constant. So, the stiffness is going to depend upon what is the extent of deformation. So, this is called as the initial stiffness. Starting with the initial stiffness, subsequent stiffness values can be evaluated, which are functions of deformation or which can be kept constant, and one can follow an incremental iterative procedure. So, these are the iterations, and this is the load increment that we have to achieve equilibrium in performing a quasi-static analysis. So, we are going to divide the load steps, total load steps, into number of small steps, and a typical interval is going to be between Tn and Tn plus 1. So, at any time Tn, the body is assumed to be in equilibrium under the prescribed loads. So, let XEL denote the quadrature points of a finite element with the internal variables epsilon p plastic strain and alpha n at time Tn. So, at equilibrium at any step Tn requires that F internal in terms of sigma n minus Fn external must be equal to 0. We apply an incremental load associated with the body force delta Bn and tractive force delta sigma bar n, such that Bn plus 1 is Bn plus delta Bn and sigma bar n plus 1 is equal to sigma bar n plus delta sigma bar n. We want to get the incremental solution which belongs to the space Vh, such that un plus 1 h is equal to un h plus delta un plus 1 h. So, this is a updated value that we want to get, together with the update in the internal variables that we have in terms of plastic strains and hardening variables. So, F internal sigma n plus 1 h minus F external n plus 1 must be equal to 0 are the discrete equations that we need to solve. The solution is obtained by an incremental iterative procedure over a typical load step Tn to Tn plus 1. Let n plus 1 k denote a value of any variable at the kth iteration. We define the incremental nodal displacements as delta dn plus 1 k. So, delta dn plus 1 k plus dn is nothing but dn plus 1 k is defined as dn plus delta dn plus 1 k. So, since UH belongs to the space VH over a typical element BE, the strain field is defined as epsilon n plus 1 k BE is equal to BE times DE of n plus 1 k. So, here we have the displacement field is denoted as a vector D, or is denoted as UH, is interchangeably representing what is the displacement that we have as a solution. So, epsilon is B times of D, where B is called as the strain displacement matrix. So, given the strain field, at each quadrature point one can compute what is the value of the stress sigma n plus 1 of k. From this we can calculate what is the element force, internal force vector Fe of internal, which is defined in terms of sigma n plus 1 of k, and then we can assemble the internal force for all the elements to get what is the global internal force vector capital F internal, which is defined in terms of sigma n plus 1 k. Now, if equilibrium is satisfied, then the corresponding value of displacement is the solution. Otherwise, we have to find out what is the incremental update in the displacement delta dn plus 1 k, and then we have to update the values from k to k plus 1, and we have to repeat the iterations. Now, as discussed, when we are going in an iterative procedure between load versus deflection or stress versus strain, during any for a given load step P1, when we are having with starting from an initial tangent, when we are finding out what is K1 of u. So, this stiffness K1 of u at any value, let us say u1, if I call this as u1 now or ua, K1 of ua, and if this is a point A. So, if we have a load deflection procedure like this, and for any given load step, let us say this is the first step that we have, which is P1, and we use the initial tangent here K0, and we try to converge, and we got this point A, and the corresponding displacement is ua. When we want to define the subsequent stiffness at this point A, this stiffness is going to be, I can call it as Ka, which is a function of ua. This can be obtained only by linearizing what is the residual force at A. So, this is the residual force that we have at Ea, I can call this as Ea. So, by finding out what is the residual force and what is the change in the residual force with respect to deflection, I can get what is this slope which is going to be my stiffness at A, Ka of ua. So, I find F internal at that point as sigma n plus 1 k, and for that current state of deformation dn plus 1 k. Now, I need to linearize by following a chain rule. So, I take the global internal force dou F internal sigma n plus 1 k by dou d n plus 1 k times delta d n plus 1 k. So, this increment in displacements is going to be my delta d n plus 1 k plus 1. So, this is simply equal to an assembly over all the elements, change in the internal force over a typical element with respect to the displacement dou E n plus 1 k times delta d E n plus 1 k plus 1. So, I am going to linearize. So, this is going to give me my slope as to how that internal force is changing with respect to the deformation, is giving me the slope that I have, which is equivalent to writing Ka of ua, and times the incremental value of the displacement in that step, which is delta d E n plus 1 k n k plus 1. So, when I put that in an integral form, I can write this as summation over all the elements B transpose E times dou sigma n plus 1 by dou epsilon n plus 1 times dou epsilon n plus 1 by dou d times delta d, because this is essentially the tangent stiffness, or is the tangent modulus, and then we are having change in epsilon with respect to dou d times delta d. So, one can rewrite this as assembly over all the elements, integral over typical element B transpose dou sigma n plus 1 by dou epsilon n plus 1 B times dx times delta d E n plus 1 of k plus 1. So, where the element tangent stiffness matrix is denoted as K E n plus 1 of k is defined as B transpose dou sigma n plus 1 of k by dou epsilon n plus 1 k times B E into dx. We can assemble that for all the elements to get the global tangent stiffness matrix, and the linearized equations now will become F internal sigma n plus 1 k minus F external n plus 1 plus k n plus 1 times delta d n plus 1 k plus 1 must be equal to 0. So, from this we can calculate what is the value of incremental displacements delta d n plus 1 of k plus 1, and this is called as the classical Newton's method. So, the algorithmic tangent modulus is defined as C n plus 1 of k is nothing but defined as change in dou sigma n plus 1 of k by dou epsilon n plus 1 of k. So, it is obtained by differentiating the return mapping update equations. So, we have in return mapping what is the elastic predictor, plastic corrector procedure. So, that from that equations we can find out what is the change in sigma n plus 1 of k with respect to epsilon n plus 1 of k. So, from a trial elastic state, which is the elastic predictor, we are having sigma n plus 1 trial is equal to modulus of elasticity E times epsilon n plus 1 minus epsilon n of p, total strain minus plastic strain in that particular step, and freezing the plastic process in that step and taking the plastic strains from the previous step, we can find what is the trial elastic state, and that stress is given by sigma n plus 1 trial. Now, considering that we are also having kinematic hardening, then one can define an effective stress or a reduced stress by defining a back stress. So, this is the back stress. So, we can have xi n plus 1 trial is sigma n plus 1 trial minus q n. Now, because the plastic process is frozen, the plastic strain epsilon n plus 1 p, the isotropic hardening variable alpha n and kinematic hardening variable in terms of backstress q n are all constants in differentiation and are taken from the previous steps. And dou sigma n plus 1 trial by dou epsilon n plus 1 is going to give you modulus of elasticity E. Now, during a plastic process, when Fn plus 1 trial is greater than 0, the plastic multiplier for a one dimensional situation is given by incremental plastic multiplier is given by delta gamma is equal to Fn plus 1 trial by E plus k plus h, where k is the isotropic hardening modulus, h is the plastic modulus or kinematic hardening modulus, and differentiating this with respect to epsilon n plus 1 will give us the linearization. So, we have change in dou delta gamma by dou epsilon n plus 1 is equal to 1 by E plus k plus h times dou Fn plus 1 trial by dou epsilon n plus 1. Now, dou Fn plus 1 trial by dou xi n plus 1 trial is nothing but the sine of xi n plus 1 trial, and dou xi n plus 1 trial by dou epsilon n plus 1 is equal to modulus of elasticity E. So, now, from here, introducing these two terms in this expression, we get the linearization of dou delta gamma with respect to dou epsilon n plus 1 will give E by E plus k plus h times sine of xi n plus 1 trial. So, the stress update for plastic loading now will read as sigma n plus 1 is equal to q n plus 1 time plus q n plus 1 minus delta gamma E divided by modulus of psi n plus 1 trial times psi n plus 1 trial. Now, differentiating with respect to epsilon n plus 1 and applying the chain rule, we can get what is the value of dou sigma n plus 1 by dou epsilon n plus 1. So, which will be equal to E times k plus h by E plus k plus h for Fn plus 1 trial to be greater than 0. So, this is the linearized value of the tangent stiffness that we get, or tangent modulus that we will get dou sigma n plus 1 by dou epsilon n plus 1. Now, if it is an elastic loading, when Fn plus 1 trial is less than equal to 0, then sigma n, it is an elastic trial state. So, the chosen value sigma n plus 1 trial is same as sigma n plus 1. So, the change in the linearization or dou sigma n plus 1 by dou epsilon n plus 1 will be simply equal to modulus of elasticity. So, the constitutive equation thus reads Cn plus 1 is equal to elastic modulus when Fn plus 1 trial is less than or equal to 0, and when Fn during a plastic process when Fn plus 1 trial is greater than 0, Cn plus 1 is equal to E times k plus h by E plus K plus H. So, there is a need to understand algorithmic boundary value problem stability by combining the return mapping algorithm with a time discretized weak form, where there is a need to look at the return mapping algorithm together with the discretized weak form. The analysis is based on adapting the energy method inspired by stability properties of the underlying boundary value problem. An algorithmic approximation is said to be stable if the discrete solution satisfies the a priori estimate of any functional L, which is a function of the un plus 1 Vn plus 1 epsilon n plus 1 E alpha n plus 1 is less than or equal to functional L of un Vn epsilon n E comma alpha n. This inequality holds for all delta t greater than 0. The algorithm is said to be unconditionally stable and if it is holding good only for delta t less than delta t critical, then the algorithm is conditionally stable. Now, if we consider a dynamic problem in the interval Tn to Tn plus 1, we are calculating the time approximation in this manner. We have an additional term that is coming from the inertia. So, 1 by delta t integral over domain rho Vn plus 1 minus Vn times eta dx. This is the, so Vn plus V is essentially the acceleration that we have un plus 1 minus un by delta t for all values of eta belonging to that admissible space of functions V. So, the functional can now be written in terms of g of sigma n plus V comma eta, which will include this inertia term unlike the previous case. So, following this time stepping procedure, one can write generalized midpoint rule of approximation, where un plus V is defined as V times un plus 1 plus 1 minus V times un. Similarly, for the velocity field, we can write V times Vn plus 1 minus V times Vn. Similarly, for stress field, we can define by a generalized midpoint rule as V times sigma n plus 1 plus 1 minus V times sigma n, where this factor V is having a value lying between 0 and 1. So, different possibilities exist for various values of V. Now, if we choose a test function eta, which is defined as delta t times V of n plus 1 V, which is equal to un plus 1 minus un, which belongs to V. Now, for various choices of V, we can write the value of Vn plus V, either Vn plus in terms of when we choose V is equal to half, then we can write Vn plus half plus V minus half times Vn plus 1 minus Vn. So, Vn plus half is defined as half of Vn plus 1 plus Vn. Then we get midpoint rule, and now with assumption of time independent forcing function, we can write T of Vn plus 1 plus V external of un plus 1 minus T of Vn plus V external of un plus the force that is coming as sigma times V times ds. So, we have sigma n plus V times dou u n plus 1 minus un by dou x times ds. So, this can be written as 2V minus 1 T of Vn plus 1 minus Vn. Now, for a case of linear elasticity, one can do the strain interpolation also in terms of V. So, epsilon n plus 1 V can be written as V times epsilon n plus 1 plus 1 minus V times of epsilon, and by choice of V is equal to half, we can write this as epsilon n plus half is equal to V minus half times epsilon n plus 1 minus epsilon n. And so, epsilon n plus 1 half is epsilon n plus half is defined as half of epsilon n plus 1 plus epsilon n, the elastic constitutive equation is written as sigma n plus V is equal to E times epsilon n plus V. From the constitutive equations, we can write what is sigma n plus V of epsilon n plus 1 minus epsilon n, and we recall that the internal work V internal is denoted as half integral over the domain E epsilon square, and we can show that L of U n plus 1 V n plus 1 comma epsilon n plus 1 minus L of U n V n epsilon n is greater than equal to 0, thereby showing that for condition for stability is that 2V minus 1 must be greater than equal to 0. So, the inspection of this result shows that a priori stability estimate holds when 2V minus 1 is greater than equal to 0, where V is going to be the step that we are going to use. So, when V is greater than equal to half, then L of U n plus 1 V n plus 1 epsilon n plus 1 minus L of U n V n epsilon n must be less than equal to 0. The algorithm is unconditionally stable. When V is less than half, then the algorithm is unconditionally unstable, then this difference becomes greater than 0 and this algorithm is unconditionally stable. When V is equal to half, then L of U n plus 1 V n plus 1 epsilon n plus 1 minus L of U n V n epsilon n is equal to 0, and the algorithm conserves exactly the total potential energy of the systems. So, the algorithms with V greater than half exhibit numerical dissipation and are only first order accurate, but the second order accuracy holds when V is exactly equal to half. So, when it is greater than half, it is going to be only first order accurate, whereas when it is equal to half, it is going to have a second order accuracy, second order accurate. So, the choice of the time stepping is based on what is the value of V, and that will decide how the stability of the system of equations is going to be based on the difference in the functionals from L U n plus 1 V n plus 1 comma epsilon n plus 1 minus L of U n V n epsilon n. So, second order accuracy holds when V is equal to half. Now, to illustrate the applicability of nonlinear numerical stability analysis, we can consider a generalized return mapping algorithm with isotropic hardening. So, the algorithmic update equations are given like this. So, we have epsilon n plus 1 p minus epsilon p is equal to delta gamma sine of sigma n plus v, right. So, and similarly alpha n plus 1 minus alpha n is equal to delta gamma, where the delta gamma is the incremental slip rate or incremental plastic multiplier, and which satisfies the Kuntakar conditions that this during that incremental step delta gamma is greater than equal to 0, f of sigma plus v and alpha n plus v is less than equal to 0, and delta gamma sigma n plus v plus alpha n plus v must be equal to 0. So, the persistency condition is satisfied, and for the plastic process to happen delta gamma is greater than 0 and the plastic process happens on the yield surface. So, here delta gamma is denoted as gamma n plus v times delta t with the parameters that v belongs to 0 comma 1 and delta or v belongs to 0 comma 1. The parameter delta specifies the point at which the consistency condition is enforced. So, it can be different from the parameter v, or it can be chosen same as parameter v. Special choices recover the classical return mapping schemes. So, when we are saying that for certain choices of delta which belongs to 0 comma 1, this consistency condition is going to be satisfied. So, using the stress strain relation and algorithmic equation, one can write what is the difference in epsilon n plus 1 minus epsilon n, and it is simply E inverse sigma n plus 1 minus sigma n plus delta gamma sine of sigma n plus v, and sigma n plus v is taken as sigma n plus half plus v minus half sigma n plus 1 minus sigma n. Now, using the condition that sine of sigma n plus v times sigma n plus v is simply the absolute value of sigma n plus v, it follows that sigma n plus v of epsilon n plus 1 minus epsilon n can be written in this fashion, and using the yield criterion and noting that delta gamma is equal to alpha n plus 1 minus alpha n, we can write what is delta gamma times sigma n plus v is going to be delta gamma times f of sigma n plus v comma alpha n plus v plus delta gamma times sigma y plus k alpha n plus v times alpha n plus 1 minus alpha n. Now, internal energy identity, using the identity that we have written alpha n plus v is equal to alpha n plus half plus v minus half times alpha n plus 1 minus alpha n. The following equivalent form can be obtained by substituting for alpha n plus v. We can write delta gamma times sigma n plus v in the following fashion, and using the stress strain relationship together with the definition of V internal, we can write the integral over domain sigma n plus v of epsilon n plus 1 minus epsilon n times dx. So, this is the internal force. So, this internal force can be written in this fashion in terms of the delta gamma sigma n plus v during the plastic process. By inserting these equations in the algorithmic counterpart of mechanical work identity and recalling the definition of the functional L u v epsilon e comma alpha, we can arrive at the term L of u n plus 1 v n plus 1 epsilon n plus 1 e comma alpha n plus 1 minus L of u n b n epsilon n e comma alpha n plus 1 as equal to integral over the domain delta gamma sigma y into dx. So, which indicates that the dissipation is greater than equal to 0 minus the quadratic form of the equation, which is greater than equal to 0 minus delta gamma f of sigma n plus v alpha n plus v times of dx. So, the stability of the numerical approximation depends on the schemes adopted in enforcing the consistency condition. The consistency is enforced when delta is equal to v, and the term delta gamma f of sigma n plus v comma alpha n plus v is taken as 0 as a result of the Kuntager conditions, and the inspection reveals that the stability holds provided v is greater than equal to half. So, for this case of algorithm, unconditional stability is holding when v belongs to half comma 1. So, consistency is enforced when delta is equal to 1. So, the result is inconclusive except for when v is equal to delta equal to 1, which corresponds to standard return mapping algorithm. So, the convexity of the yield function implies that this delta gamma f of sigma n plus v comma alpha n plus v must be less than or equal to 0. Now, since consistency condition is to be satisfied and Kuntager conditions are satisfied, the second term in this equation is always going to be positive. So, one can conclude that the left hand side is going to be non-positive. So, both schemes include classical return algorithm which are unconditionally stable. So, for specific choices of v and delta, when delta is equal to v or when delta is equal to 1, one can show that the classical return mapping algorithm is also conditionally stable, and the stability is governed for the factor of choice of value of v, and when we choose value of v is equal to half, then we are going to get second order accuracy and it is going to be stable, and when v is less than half, it is going to be unconditionally unstable, and when v is greater than or equal to half, it is going to be only unconditionally stable only of first order accuracy. So, one can choose different values of V and find out the stability by evaluating what is the value of this difference in functional between the time steps to get a minimization type of a problem that is conditionally stable. Now, in summary, in this lecture we have looked at elastic plastic boundary value problem and formulated it using a weak form approach, and understood how to calculate the element level internal force and external force, and the equilibrium equations which involve the nonlinear equilibrium equations are solved by using an incremental iterative algorithm by following a Newton iteration, and we have understood how to linearize to get the tangent stiffness and or the tangent modulus, and the stress updates are performed using return mapping algorithm together with a consistent algorithmic tangent modulus. And when we are doing an update over a time step, we understood that the numerical stability can be analyzed through finding out what is a discrete energy method for a time discretized system, what is the difference in the energy when we go from one step to the other. And we have seen that conditional stability is achieved for a parameter V greater than or equal to half when it is going to be unconditionally stable and second order accurate. Thank you for your attention.